Welcome to The Explainer. Today, we're looking at a fascinating paradox in nuclear physics. It's a process that genuinely seems to defy the very laws of consumption. Imagine a car that actually produces more gas than it burns while you drive it down the highway. Sounds like magic, right? Well, in the world of nuclear engineering, this isn't magic at all. It's a very real, scientifically proven concept. So let's jump right in and uncover the mechanics behind what is arguably one of the most brilliant engineering solutions ever devised.
Okay, starting off with Section 1, the cost of enrichment. To really grasp why this magic trick is so revolutionary, we first have to look at the massive material problem at the heart of traditional nuclear power. Looking at our source data, the raw numbers are, well, honestly, they're kind of staggering. In nature, uranium only has a tiny 0.7% of the fissile stuff we actually need to power most reactors, so we have to enrich it. Let's say we want to create fuel for a fast reactor that requires 14% enrichment. To get just 100 kilograms of this enriched fuel, which has 14 kilos of uranium-235 and 86 kilos of uranium-238, we have to start with a whopping 2,000 kilograms of natural uranium. Do the math there, and you're left with 1,900 kilograms of uranium-238 that is simply rejected, left entirely unused.
Which brings us to a really pointed question from our source material. For every 100 kilograms of 14% enriched fuel we get, 1,900 kilograms of uranium is just sidelined. Is that justified? And keep in mind, practical enrichment often exceeds 20%, meaning that rejected pile gets even bigger, all while we're rapidly burning through our scarce uranium-235. This massive, glaring inefficiency is the exact driving force behind the need for a radically better system.
And that brings us to Section 2, the breeder reactor concept. So how do we pivot from this massive problem of wasted uranium to our mind-bending solution? Enter the breeder reactor. By using a very specific geometry and combination of materials, a breeder reactor's fissile production rate actually outpaces its consumption rate. How? It basically takes that 1,900 kilograms of wasted uranium-238, what we call fertile material, and physically converts it into highly valuable fissile plutonium-239. It is literally making its own fuel for the next cycle while it operates. It eats and somehow creates even more food in the process. Pretty wild, right? Let's dig into how that actually works in Section 3, the neutron budget, eta. How is this physically possible? Well, it all comes down to the underlying physics of the reactor core and a very strict atomic accounting system. We track this using a specific parameter, represented by the Greek letter eta. Eta is simply the average number of neutrons produced for every neutron absorbed in the fissile material. You can really just think of eta as our total neutron budget, because if we aren't producing enough neutrons during fission, the whole breeding concept just completely falls apart. So let's break down this budget logically. Every time an atom splits, it releases neutrons, and we've got to spend them wisely. First, exactly 1 neutron is needed just to pay the bills. It has to go split another atom to keep the chain reaction alive. Then, we have to pay taxes. These are unproductive losses. Neutrons leaking out of the reactor or getting absorbed by the wrong things. Finally, whatever is left over, that's our pure profit. That's what we can use to capture in our fertile uranium-238 to breed brand new plutonium fuel. And this perfectly illustrates the golden rule of breeder reactors. Mathematically, for breeding to even happen, eta has to be strictly greater than 2. Why? Well, you need 1 neutron to sustain the chain, plus a fraction of a neutron lost to taxes or leakage, which means you absolutely need at least 1 full neutron left over to create that new atom of fuel. If your eta isn't well over 2, you're running a deficit, and breeding is just a no-go. Which leads us perfectly into Section 4, why fast reactors win. Now that we know this strict mathematical rule, let's look at the hard engineering reality. Take a look at the plot lines on this graph. If you draw your eyes all the way over to the right side, that's the fast reactor neutron energy range, with a flux around a few hundred kiloelectron volts. Look at that dramatic spike for plutonium-239. In this high-energy fast range, its eta value shoots way above 2, just completely leaving all the other fissile materials in the dust. And the raw data totally backs this up. Compare standard light water thermal reactors with fast breeder reactors. When we look at plutonium-239 in an oxide-fueled fast breeder reactor, the eta value hits a massive 2.45. This high eta is the exact lucrative payoff that justifies building fast reactors in the first place. It gives us plenty of extra neutrons to absorb into that uranium-238 blanket surrounding the core, crowning plutonium-239 as the absolute undisputed fissile champion for this job. Okay, moving on to Section 5, measuring success, breeding ratio. So we've got the theory down, and we know the right fuel. But how do engineers actually measure the economic success of these things over a typical cycle? The primary metric is the breeding ratio, or BR. It's a simple but super powerful equation. Just take the fissile mass produced during a given period and divide it by the fissile mass lost in that exact same period. If this ratio is less than 1, you just have a standard conversion reactor. But if you can get that ratio greater than 1, you have successfully crossed the threshold into a true breeder reactor. You're making more fuel than you consume.
And here is where it gets incredibly exciting. In principle, fast breeder reactors can achieve a breeding ratio of up to 1.4. Think about what that actually means. For every 10 units of fuel it consumes to make electricity, it produces 14 completely new units of fuel. That excess 0.4, that is your breeding gain. It is the exact mechanism that turns those massive stockpiles of rejected, unused uranium into an absolute goldmine of future energy. Which brings us to our final section. Section 6, the payoff, doubling time. So what is the ultimate long-term payout of operating a breeder reactor system over decades? Our source text uses this brilliant financial analogy to explain this, and I absolutely love it. Think of the fuel you initially put into the reactor as your principal investment. Because your breeding ratio is over 1, you're earning a steady interest rate paid out in brand new fuel. Over time, that interest accrues. Eventually, you generate enough extra fuel on top of feeding the original reactor to completely match your initial investment. You get back the principal plus an interest equal to the principal.
In the nuclear physics world, we call this the doubling time. It's defined as the operating time required for a breeder reactor to produce enough excess fuel to power an entirely new, identical reactor. The source notes that while present-day fast breeder designs might take more than 20 years to achieve this, advanced designs are actually aiming to slash that doubling time down to just about 10 years. Imagine that. Every 10 years, your power plant literally spawns enough excess fuel to give birth to a completely free sister plant.
And this opens up some massive global possibilities. Our source explicitly highlights that fertile thorium fuel can also be bred into fissile uranium-233 using these fast reactors. For regions with huge, untapped deposits of thorium, like India, whose future nuclear program is expected to be based exactly on this concept, this technology is a total game changer. So I'll leave you with this thought. If we can master the fast reactor and shrink that doubling time down to 10 years, converting the world's unused thorium and uranium into endless fuel, is this the ultimate key to humanity's energy future? It's a fascinating question, and the physics say it's entirely within our grasp. Thanks for joining me on The Explainer, and keep exploring.